Hi, this is Kenny speaking. I'm from the National United University Department of Energy Engineering. In the previous section, we will talk about the test station and the component of each test station, the function of each component. And in this section, we're going to talk about the mass flow rate of the reactant during the test, how to determine the mass flow rate based on the output current. Because from Faraday's law, the mass flow rate actually should be dependent on the output current, either stack or the single cell.
Let's consider a stack. The stack will contain n cells. So many number of single cells stacked together in series. And then the oxygen was flow from the lower left-hand corner in, and then the upper right-hand corner out, and with the mass flow rate or the mass flow rate of MO2. And the hydrogen was flowing in from the lower right-hand corner and then coming out from the upper left corner out with the mass flow rate of MH2. And then the current is coming out, connected from a 2N plate current collector with a current of I. Since the single cell was connected in series in a stack, so the current will flow through each single cell, and then the minimum, the lowest current output will determine the total stack output current. They should be the same. Based on the current output from the Faraday's law, we're able to calculate the flow rate, the required flow rate for the hydrogen or the oxygen. The flow rate can be divided into, can be classified into the molar flow rate, mass flow rate, volumetric flow rate, or sometimes being used, quite often used is the standard liter per minute, because with this unit, for 1 kilowatt of fuel cell output power, you require generally is about 10 liter per minute. So it's the exact number based on the fuel cell operation condition though. Now let's consider the hydrogen flow rate first. For the hydrogen, the reactant reaction taking place on the anode side of the fuel cell is 1 molar of hydrogen will be released 2 molar of electron. So based on this, we're able to calculate for a single cell the hydrogen molar flow rate of the single cell from the Faraday's law. Is I divided by NF. The I is the current flow through or output from the single cell. The unit is M, or coulomb per second. And then the N is equivalent. That means per mole of hydrogen consumed, how many mole of electron will be released. And the times the Faraday constant, that means each molar of electron is equal to 96,500 coulomb. So from the unit, the coulomb will be cancelled each other, and the mole electron will be cancelled out. So this will left the molar hydrogen per second. So from the I divided by NF, if we know the current output from the fuel cell, you're able to calculate how much the molar flow rate of hydrogen need theoretically to able to generate current I. This is for single cell. For a stack, usually the hydrogen will be equally distributed into each single cell, but the output current still will be the same, I, not change at all. But what is beneficial to stack so many single cells together? The point is will increase the output voltage. The output voltage for a stack equal to the total sum of single cell voltage. So in this case, you can by stack the single cell together, instead of come out with single cell voltage maybe 0.5 or 0.7 volt, you may come out with an output voltage maybe 12 volt or 46 volt, depends on how many single cells stacked together, although the current is still the same. So the hydrogen flow rate for a stack with an N cell, then you need to time number of cell, N cell, in the formula. You will know how much the hydrogen required for a stack. So the molar flow rate for the hydrogen can be calculated by I divided by 2F and the times N cell. For the oxygen, then you'll be able to the same, but the number of electrons is 4, so you had to divide by 4F instead of 2F, because 1 molar of oxygen consumed the required 4 molar of electron. And then the product of hydrogen also can be calculated, the molar flow rate. But how about the mass flow rate? Since we already know the molar flow rate from the previous slide, we're able to calculate the mass flow rate by simply use a molecule weight times molar flow rate. So then we can able to calculate the hydrogen, oxygen, and water mass flow rate. And then for the volumetric flow rate, since all the fuel cells operate at a relative lower temperature, lower pressure, or the temperature, so the all the gas can be treated as ideal gas. So we can calculate those volumetric flow rate from the molar flow rate, assume all the gas is ideal gas. So the volumetric flow rate can be calculated by using the ideal gas law. But over here we consider as a standard condition at the pressure equal to 101.3 kilopascal. That's about 1 atmosphere, and the temperature is 15 Celsius degree. That's 288 Kelvin. We assume all the gas is at this condition is ideal gas. We can apply PV equal to nRT. So we're able to calculate the molar volume at a standard condition. So the Vn is a molar volume. The R equal to 8.315, and times the temperature divided by pressure. We end up with per mole of ideal gas at this condition is about 0.02365 cubic meter, or 23.65 liter per mole. So from previous slide, we know how to calculate the molar flow rate from the output stack current. Then over here we know the molar volume for hydrogen, so we can able to calculate the volumetric flow rate of the hydrogen by simply times the Vn times the molar flow rate. So over here you end with liter per second, the unit. So the volumetric flow rate over here, we are talking about the liter per minute instead of liter per second. So in the equation, we need to times 60 over there, and then we end with a prefix number is 0.00735. So from this equation, at this 15 Celsius degree, 1 atmosphere, as long as you know the output current and the number of single cells in a stack, you're able to calculate volumetric flow rate of hydrogen by simply the current times the N cell times this number. Then you can know the volumetric flow rate of hydrogen. And the oxygen, you can do the same thing with this prefix number. So from the ideal gas law, with this prefix number, this simplified equation, as long as you know the current and the number of cells, you're able to calculate the flow rate of a stack. So beside the volumetric flow rate, we can able to calculate a molar flow rate with this prefix number, and then molar flow rate, mass flow rate in gram per second, volumetric flow rate in cubic centimeter per second, or SLPM, that's means standard liter per minute. With different other prefix number, you can calculate for the oxygen and the water. This is the theoretical volume flow rate based on the output current, but in reality, the operation, we need to introduce another number we call the stoichiometric ratio. Stoichiometric ratio S is defined by N act divided by N0. The N act is the actual molar flow rate, and N0 is the theoretical molar flow rate. And this one, stoichiometric ratio, can be also defined by a mass ratio for the actual mass flow rate divided by theoretical mass flow rate, or volumetric flow rate. The S always greater than 1 because there's some kind of loss during the operation. So it's usually greater than 1. We consider a cell. The red part is the electrode, the green is a membrane, and the brown is a gasket or the sealing, and the gray portion is a graphite plate. In the theoretical calculation, we assume the hydrogen, the gas coming in the cell, and then there's nothing leak out, it's stop, no gas out. So this is theoretical flow rate. As long as the hydrogen was consumed in the cell, in the electrode surface, then the pressure will be decreased and had more hydrogen will flow in. So the flow rate coming into a single cell, like this, is a theoretical flow rate. But in reality, sometimes there's a gas coming out during the practical operation. So the actually flow rate is greater than theoretical flow rate. This is particularly true for the air, because the oxygen in the air only about 21%. So if you control, if you feed in the air based on theoretical consideration, you end up with a very, very low efficiency, because that to the end of the electrode or the cell in a stack, all the oxygen was consumed. What you left is nitrogen. So there's no reactant, and the electrode exposed to the nitrogen had nothing to coming out. So you waste a lot of electrode area, and then for a given cell, the output will be much less than what you expect, because there's a concentration over potential. There's no oxygen in the air, then nothing will happen, and then you will suffer a lot of voltage drop. So during the air side, on the air side, the stoichiometric ratio usually keep at a 2 to 4, greater than theoretical consideration. So make sure you got sufficient air, the oxygen concentration in the cell stack. Also, the air kind of free, so you can give a little bit more without any problem. For the hydrogen side, the stoichiometric ratio control about 1 or 1.1, because the hydrogen is fuel and it costs money, and you don't want to release hydrogen into the environment. It might be dangerous also. So that's a stoichiometric ratio on the hydrogen side will keep about close to 1. But for the air side, usually keep about 2 to 4. For the fuel utilization, we talk about the stoichiometric ratio of hydrogen side, but on the hydrogen side, we talk about the fuel utilization. Can be calculated by this equation. The N series, that means the theoretical hydrogen flow rate, divided by actually fitted in the hydrogen flow rate. There'll be N series plus N loss, maybe hydrogen loss, and then there's a purging. The purging depends on fuel cell operation, the different operating mode. For instance, there's a dead end and a recirculation mode. The dead ends, that means like this, we've been this one, and the left will be the cell stack, and the right hand side is a hydrogen tank. The hydrogen will feed through the mass flow controller, feed into the stack, and then normally the exhaust gas valve was closed normally. That's called the dead end mode. And then the recirculation mode, that means between the output fuel line and the input fuel line, that's connected with the pump or compressor, circulate the fuel, so make the fuel keep flowing through the during the operation. The pump or compressor had to be explosive proofed. A pump or compressor, you cannot use commonly use the pump. You had to be careful. So for the dead end and recirculation mode, the N fuel equal to theoretical flow rate divided by theoretical plus possible loss. Usually, since there's no fuel going out, so only possible will be the leakage or crossover. Also, we try to keep that loss as minimal as possible. And for the other mode is a dead end with purging. The dead end with purging, the similar dead end mode, but the calculation we had a purging factor considered. This means sometimes for a given period of operation, the valve may be open for maybe a few seconds and release the hydrogen into the atmosphere. So keep the hydrogen in the cell with sun circulation, can blow out the water, maybe cross over to the anode side. Although the water should be generated on the cathode side, but sometimes it may be leaked through to the anode side. That may cause some blockage of the airflow if there's no airflow. So sometimes you need to get the hydrogen open for a very brief time to blow off all the possible oxygen and the water block inside the anode side. So there's a purging. The amount of hydrogen purging will be equal to the flow rate when the valve open, the hydrogen flow rate millimolar per second times the purging time. Each time how long the valve will open. For instance, this may be open for 2 seconds, and then how many period of time the valve may be open. That means this example will be 60 seconds. Every 60 seconds the valve will open for 2 seconds. So this one should be approximately flow rate will be about 1/30 millimolar per second. Actually should be 1/31 for a period actually about every 62 seconds you had 1 millimolar of the hydrogen were going out. So the fuel utilization mode, there's a different mode. For flow through mode, the theory will be N series divided by N theoretical times plus N loss. That means that the hydrogen will be keep flow through the cell and then discharge. Use hydrogen will discharge into the atmosphere. For the dead end mode, usually it's not too many cells operate at the dead end mode. For the flow through mode, usually during the test is a small a small single cell, maybe 5 watt or 1 watt, the fuel cell, single cell, the hydrogen flow rate is very small, so maybe discharge into atmosphere without any dangers, and then the cost count into those kind of operation. But for the big like kilowatt fuel cell, usually the circulation mode was adopted because with a pump or circulation pump compressor will be circulate hydrogen inside the fuel stack, will be increase the fuel cell operation efficiency, and without discharge into too much hydrogen into the atmosphere. But sometimes the circulation mode also with purging also, because occasionally there's a water accumulated, so you need to purge out, discharge out through the system. For the 100 watt below, maybe 10 watt, those fuel cell stack usually using the purging mode without circulation, because the circulation with the pump or compressor will be also consume some electricity. So we don't want to waste too much electricity on that, because the fuel cell only 100 watt, 10 watt small output power cannot supply the electricity for pump, circulation pump. So far, this unit will already talk about how to do the flow rate of the reactant for a stack, and then introduce a stoichiometric ratio. During the fuel cell operation, we had to consider this factor and the fuel utilization. And the fuel operation mode, all those flow rate calculation depends on the operation mode. For the flow through mode, that's usually for the university academic research, we have small single cell, then we usually use the flow through mode. And for the then with purging, that usually for a stack about 10 watt to 100 watt, that small cell, maybe with a purging mode, occasional discharge of hydrogen will be increase the fuel cell efficiency. And for the large kilowatt above cell stack, usually we had a dead end with a recirculation mode, but sometimes also with occasional purging mode.